A good experiment can give you the correct data. A good instrument can measure it correctly. But one wrong turn can still change the meaning of the final result. And in electrochemistry, this happens more easily than we may think. Two words are especially important: capacitance and capacity. They sound almost the same. Both are related to stored charge, but they do not describe the same thing. And once these two are mixed, the problem does not stop with the unit. The measuring or estimation of energy can change, and the meaning of power can change. Even the comparison between two materials can become wrong. In the previous video, we saw that different materials can store charge in the different ways. Now we move one step ahead. Once we know how the charge is being stored, how should we report that charge correctly? And in this video, we will connect four very common units: farad, coulomb, ampere-hour, and watt-hour. And by the end, the aim is very simple. Whenever you see a electrochemical value, you should be able to tell what that number actually represents. So let us begin with the most basic difference. Capacitance is not capacity. So let us first keep both terms side by side. On one side we have capacitance. On the other side we have the capacity. So start with the capacitance. The capacitance tells us how much charge a device stores for a given voltage. The basic relation is C equals to Q divided by V. Here C is a capacitance, Q is charge, and V is voltage. So the important point is that capacitance connects charge with voltage. If a device can store more charge for a same voltage change, its capacitance is higher. Its unit is farad, can be written as F. Now move to the capacity. The capacity tells us the total amount of charge delivered. For constant current, we can write Q equals to I multiplied by T. Here I is a current and T is time. So the capacity connects current with time. This is why battery are commonly reported in ampere hours or Ah. Now look at the difference carefully. For capacitance, voltage is the part of the meaning. For capacity, we are interested in total charge. So these two statements are not same: charge per volt and total charge. This is the basic idea behind the complete video. For capacitors and supercapacitors, farad is commonly used. For batteries and strongly battery type materials, ampere hour or milliampere hour is commonly used. So keep this one line in mind. Capacitance tells us charge per volt. Capacity tells us the total charge. Once this is clear, the next slide become much easier. Let us understand the farad properly. A farad is a unit of capacitance, and its meaning is very direct. 1 farad means 1 coulomb of charge for every 1 volt. So 1 farad equals to 1 coulomb per volt. Now look at the simple capacitor shown on the slide. We have charge Q, we have voltage V, and capacitance tells us how these two are connected. Let us now use the value shown here. The capacitor has a capacitance of 100 farads. Its operating voltage is 2.7 volts. We know Q equals to C multiplied by V. So 100 multiplied by 2.7 gives 270 coulombs. And this result is quite useful. The capacitance is 100 farad, but the stored charge at 2.7 volt is 270 coulomb. So a farad is not simply another name of coulomb. Farad tells us how charge changes with voltage, and this also tells us something else. If we know only the capacitance, we still do not know the full energy of the device. We also need the operating voltage or potential, and this becomes very important for supercapacitors. A device may have a high capacitance, but voltage still play a major role in its final energy. We will come back to this near the end. For now, the important message is a large farad value means more charge can be stored per volt, and the farad measures capacitance, not battery capacity. Now we move from capacitance to capacity. Here we are no longer talking about charge per volt. We are talking about total charge delivered. For a constant current, Q equals to I multiplied by T. So we need two things, current and time. If the current is known and we know how long it flows, we can calculate the total charge. Now look at these unit relations. 1 ampere hour equals to 3600 coulombs and 1 milliampere hour equals to 3.6 coulombs. This is important because it shows that coulomb and ampere are both describe charge. Coulomb is a SI unit of charge. Ampere hour is very useful for batteries. Now look at the battery example shown on the slide. The battery delivers 2 ampere for 3 hours. So 2 multiplied by 3 gives 6 ampere hours. Now convert this into coulombs. So 6 multiplied by 3600 gives you 21,600 coulombs. So the same delivered charge can be written as 6 ampere hour or 21,600 coulomb. Nothing about the battery has changed. Only the unit has changed. This is different from the farad. Coulomb and ampere hour tells us the total charge. Farad tells us the capacitance. So this slide gives us another very simple line. Capacity is a total charge, not the charge per volt. Now we add mass to the calculations. In research, this is very important. Suppose two electrodes contain different amounts of active material. The electrode with more material may naturally store more charge. So comparing only the total value may not be fair. For this reason, we often divided the result by mass of the material. Let us first look at a specific capacitance. The relation shown here is C specific equals to C divided by M. In simple word, capacitance divided by mass. And the common unit is farad per gram. So specific capacitance tells us how much capacitance we get from each gram of material. It may also be reported per area or per volume when that is useful. So now look at the specific capacity. Here we divide total charge by mass. The relation is Q specific equals to Q divided by M. This can be reported as coulomb per gram or milliampere hour per gram. Now this is where we have to be careful. Both values may contain per gram, but they still do not mean the same thing. Farad per gram describes the capacitance per gram. Milliampere hour per gram describes the total charge per mass. So simply looking at the per gram does not make two values directly comparable. While reading a paper, always check what quantity is being divided by mass. Also check which mass has been used. Is it the active material, one electrode, both electrode, or the complete device? That small detail can change the reported value. So before comparing two numbers, check the unit and check the mass basis. That gives a much better comparison. Now we come to one of the most useful slide in this video. The same supercapacitor can be described using farad, coulomb, ampere hour and watt hour. At the first, this can look confusing, but actually each unit is telling us different part of the same story. The device shown here has 100 farad capacitance and an operating voltage of 2.7 volt. Its capacitance is already known, 100 farad. Now let us calculate the stored charge. We use Q equals to C multiplied by V. So 100 multiplied by 2.7 gives you 270 coulombs. Now take the same charge and convert it to the ampere hours. So 270 divided by 3600 gives you 0.075 ampere hour. That is 75 milliampere hour. So far the same device has gives us three numbers: 100 farad, 270 coulomb and 75 milliampere hour. But we are not finished here. Now calculate its stored energy. For an ideal capacitor, E equals to 1 half CV square. So putting in the values, 1 half multiplied by 100 multiplied by 2.7 square gives you 364.5 joules. When we convert that to watt hours, we get about 0.101 watt hour. Now see what has happened. The device is still exactly the same, but we can describe it as 100 farad, 270 coulomb, 75 milliampere hour, and 0.101 watt hour. And all these numbers have different meanings. Farad tells us the capacitance, C and Ah tells us the charge, watt hour tells us the energy. And this is why comparing only the size of the two numbers can be misleading. A number has very little meaning without its unit. So, whenever you see an electrochemical value, first look at the unit. The unit tells you what the number is actually describing. Now, let us come to something very practical. This part matters when we write a paper, thesis, report, or presentation. Look at the left side first. For capacitance, use farad or farad per gram when the value has been divided by mass. For capacity, use coulomb, ampere hour, or milliampere hour. And when the capacity is divided by mass, you can use milliampere hour per gram. Also state the potential window. And when you compare two materials, make sure that both values have been calculated in a similar way. Now, look at the mistakes shown on the right side. On one common error is using farad when the actual value is farad per gram. These are not the same. Another error is using farad per gram when the result should be in milliampere hour per gram. Again, the number may look fine, but the physical meaning has changed. Here is a very clear example. 150 farad per gram does not mean 150 milliampere per gram. Another mistake is leaving out the voltage window that removes important information about the measurement. Then we have direct comparison between farad per gram and milliampere hour per gram without proper conversion or proper explanation. That can give the reader a wrong idea about performance. And one more point is very important. Always state whether the result belongs to a material, a electrode, or a full device. Why? Because the mass used in the calculation can be different. So the same experimental data can appear very different if the calculation basis is changed. This is why good scientific reporting is not only about getting a higher value or high value. It is about telling the reader exactly what that value means. Now we can connect everything with energy and power. For capacitor, the energy relation is E equals to half CV squared. So capacitor energy depends on the capacitance and voltage. But look carefully at the voltage. Voltage is squared. This makes voltage very important. This means that a high capacitance alone does not tell us the full energy. The operating voltage also has to be considered. This is especially important in supercapacitors. If the stable voltage range can be increased safely, the energy can rise strongly because of the V squared term. Now move to the battery side. For a battery, the energy can be written in a simple form as energy is approximately equals to stored charge multiplied by average voltage. So battery energy depends on how much charge is available and the voltage at which that charge is delivered. Now, we can see why using the correct quantity is so important. For capacitor, capacitance and voltage are used. For battery, stored charge and average voltage are more useful. Now, look at power. Power equals to energy divided by time. Power tells us how quickly the stored energy can be delivered. And this gives us three very important results. High capacitance does not automatically mean high capacity. High capacity does not automatically mean high power. And voltage has a strong effect on energy. These are different part of device performance. A device may store a large amount of charge but release it slowly, and another may store less energy but deliver it much faster. So, capacitance, capacity, energy, and power should not be used as if they are same thing. Each one tells us something different, and each one needs the correct equation. So now let us connect the full video in few clear points. Capacitance and capacity are different quantities. Capacitance tells us charge per volt. Capacity tells us total charge. Farad measures the capacitance, and 1 farad means 1 coulomb per volt. Coulomb and ampere-hour measure the charge, and 1 ampere-hour equals to 3600 coulombs. When we divide these values by mass, the difference still remains. Specific capacitance is not specific capacity. Farad per gram and milliampere-hour per gram should not be treated as the same quantity. The same device can also be described in several correct ways. Farad tells us the capacitance, coulomb and ampere-hour tells us the charge, watt hours tells us the energy. So the most useful habit while reading any electrochemical result is always check what quantity is being reported. Then check the unit, check the voltage range, check the mass used in the calculation, and check whether the value belongs to a material, a electrode, or a complete device. Because in electrochemistry, a large number is not enough. The number has to be represent the right quantity, and that is the main message of this video. Capacitance is the charge per volt. Capacity is the total charge. They are connected, but they are not the same. And once this difference is clear, capacitance, capacity, energy, and power become much easier to understand correctly.